So now we are going to design the front end for this receiver in 45 nanometer CMOS process. So I have written the specification for the receiver as we derived based on the IEEE 802.11g standard. And we are going to design an LNA, which is the first block in the receiver, so as to meet these specifications of the receiver. So here the important specs are this noise figure, while making sure we meet the linearity. And this linearity spec of -16 dBm at maximum gain can be a little difficult to achieve in a CMOS process. So we are trying to see how it can be done. So we are going to make few design choices. We will assume that the maximum inductance which is possible in this process is 6 nanohenry at 2.5 gigahertz. So beyond that, the SRF of the inductor will become too low and the Q will also start dropping. Also, we are budgeting a current of 5 milliamps for the LNA. So this is going to be a power constrained design. So we'll try to see what is the best noise figure we are able to achieve while meeting the linearity spec and consuming 5 milliamps from 1.1 volt supply. So now we are going to design an LNA for the given receiver specification. And we are going to choose the inductively degenerated common source amplifier topology for the LNA design. So the first step is going to be to choose the input element. So this input element, we are choosing to have the minimum channel length in the process. So this is a 45 nanometer CMOS process. We are choosing channel length of 45 nanometer. The minimum channel length is going to give us the maximum FT and the minimum undesired parasitics. So we are choosing a finger width of 1 micron. And now we want to find out what is the optimum gate source voltage for this input element. So for this design, we are budgeting a headroom of 250 millivolts for this input element. So the optimum gate source voltage we are going to choose in such a way that the input element is going to have the minimum GM3. GM3 is also the third derivative of IDS versus VGS relationship for this MOSFET. So it ensures that the spurious terms because of the third order nonlinearity are as low as possible, at least due to the gate swing. So to find the optimum VGS, which gives the minimum GM3, we need to find out what is the derivative of GM with respect to VGS. And then we take one more derivative to find the VGS for which GM3 is 0. So let us start the simulation. So we are going to do a DC operating point simulation for this. And we have chosen a initial value of VGS to be equal to 0.6 volts. So we can see that under this initial condition, we are getting a GM of 405 microsiemens. So we are now going to sweep this VGS to find VGS which gives GM3 to be 0. So to do that, we need to first take the GM as one of the output in this simulation. Okay, now we are going to sweep this VGS from 0.5 till 0.7. So this is the GM versus VGS curve we have got for this MOSFET. Now let us take the first derivative and the second derivative. So this is the GM. This is the first derivative of GM. We can see that there is a maxima for the GM2, and at this maxima point of GM2, we see the GM3 is becoming 0. So if we are operating at a VGS which is close to the GM3 equal to 0 point, then we are going to get very low contribution due to the third order nonlinearity. So we will be choosing a VGS which is around 0.59, which will give a very low value of GM3. So now we have got the optimum VGS value for this MOSFET. So the current density is fixed. The only thing to vary is now the width of the MOSFET. So here we can see that it is consuming only 34.8 microamps, whereas the budget given to us is 5 milliamps for the LNA. So we are going to scale the number of fingers and the multiplier such that overall this MOSFET consumes close to 5 milliamps of current. So let's increase the number of fingers to 10, multiplier to also 10. So now we can see that it is consuming close to 5 milliamps. So now the biasing as well as the sizing for this input element has been optimized. Next step is to add a cascode element. So for simplicity, we'll choose the same device sizing for the cascode as well. And now we will change the overall supply for this series combination of cascode and the input element to be same as the VDD, which is 1.1 volt. Because the assumption is that there is going to be a inductive load for this LNA. So the drain voltage of the cascode is going to be around VDD. Now, since this cascode is going to have a 250 millivolts as the source voltage, so we may have to also increase the gate voltage of cascode by 250 millivolts as compared to the input element. So although there will be some impact of the body effect, which will change the VT of the cascode, for now, we'll choose this value to be 250 millivolts above the gate source voltage of the input element. Call it VCAS. So let's choose this to be equal to 0.84. So now we can see that the drain voltage of the input element has increased slightly to 0.265, and overall current in this series combination is close to 5 milliamps. So the cascode voltage can be further optimized. Right now we will just leave it to this value and go ahead. So the next step is to add an inductive element at the source of the input element so as to cause inductive regeneration, and this inductive regeneration will result in a real part in the input impedance. So we will add an inductor, and here we also have an IND Q element where the loss of the inductor can be directly included by just mentioning the quality factor at the given frequency. So let's say we have a series inductance at the source node to be LS with a Q of 10. So we'll add this element, and now we want to check the input impedance. So for that we will add a port to the gate, and this port will help us in performing an S parameter simulation. So using the S parameter simulation, we can find out what is the input impedance. The port should be AC coupled, otherwise it is going to change the DC voltage at the gate. So now we are AC coupling the port to the gate and DC is supplied by this DC source. So this LS value depends on the FT of this MOSFET. So let us just find out what is the FT of this MOSFET. So the model has a parameter called FUG, which gives the FT of the transistor. So here we are getting an FT of 105 gigahertz. So for this 105 gigahertz of FT, we are going to get a LS value of around 76 picohenry. We'll choose this to be 76 picohenry. And also perform a S parameter simulation. In our frequency band. So now we can plot the real and the imaginary part of the input impedance. So we can see that the real part is around 90 ohms, whereas the imaginary part is minus 732 ohms. So real part is coming out to be more than what we expected. Reason being the LS is also having a small series resistance. In addition to that, the MOSFET also has some CGD. So because of this effect of CGD and some series resistance in the LS, the actual real part is coming out to be higher than expected. But a more concerning issue is this huge reactive impedance. Now to compensate this high reactive impedance, we may have to use a high value of series inductance at the gate side. Now this series inductance we can use as a off-chip inductance, because off-chip inductance will be having very high quality factor, but the constraint is that those off-chip inductance cannot be very high. So we'll find that if you want to compensate this 730 ohms of reactance using inductance at 2.45 gigahertz, then the inductance value should be around 47 nanohenry, which is very high. So we are going to add some extra capacitance between the gate and source so as to reduce the value of inductance which will be required to put in series on the gate side. For that, let us estimate what is the capacitance which is already present. So we can find CGG, which is the total capacitance at the gate node. You can see it is around 78 femtofarad. So if we want to reduce the input inductance, let's say by close to 10 times, so that this 47 nanohenry becomes somewhere close to 5 nanohenry, we will also increase the CGS by close to a factor of 10. So let us add an extra capacitance at the gate side. (700 femtofarad). And since we are increasing the CGS by factor of 10, we may also have to increase the LS also by close to factor of 10. So we have a 76 picohenry. Let us increase by factor of 10 to 760 picohenry. Now again, let us plot the real and imaginary part of input impedance. And now we can see that the real part is around 43 ohms, close to 50 ohms what we wanted, and imaginary part is minus 81 ohms. So this minus 81 ohms can be easily compensated by a series inductance. At 2.45 gigahertz, we need an inductance of around 5.2 nanohenry to compensate this reactance. So we will add a series inductance here. And since this inductance is going to be off chip, I am not including any series resistance for this inductance. Now we can directly plot the S11 at the input, and we can see that it is well below 20 dB. So the input matching has been achieved. Now let us add the biasing at the drain. We will add an inductor here with a quality factor of 10. And so as to maximize the RP at the output, let's choose the maximum inductance which is possible. And we may need some extra capacitance to tune this inductance. Let's call it CP. What is V out? Now we need to find the optimal value of CP so as to get the proper tuning at the output. So we can now add an AC analysis to get the gain for this circuit. So the AC analysis can be done with the help of a small signal parameter here. So I will add a AC source with magnitude of 1. And we can add an AC analysis here. Right now, the capacitance at the output is 0. So we will try to see how much is the gain we are getting. So the gain is somewhere around 17.8 dB, but we can see that this is not properly tuned at the output. So we will run this AC simulation by sweeping the design variable CP at the center frequency of 2.45 gigahertz. So now we can plot the gain as a function of CP. So we can see that at CP value of 660 femtofarad, we are getting a gain of 35.8 dB. So now we can check the gain in the frequency band. So we can see that we are getting a very good more than 35 dB of gain in the entire band. Also, let us just verify the matching again. The matching has degraded. Now it is minus 13 dB, but is still better than 10 dB in the entire band. So again, input matching network can be further optimized after we have connected the output network because of some parasitic capacitance which is present between the terminals of the cascode and the input element. So there is a impact of output load at the input matching network. The impact is minimal, but still it is changing the input matching. So for now, This is good enough for our application. So we'll go ahead and try to find what is the noise figure and the linearity for this circuit. So for the noise figure, we can perform a noise analysis. So we'll choose the output node. And the input port. Okay, so we can see that the noise figure is really good. It is close to 1 dB. And this is what we expect from a inductively generated common source LNA. Since the GM of our input element is pretty high, around 50 millisiemens, and at the same time, there is passive amplification at the input because of the Q of the input matching network. We are getting very good noise figure. So let us add the noise figure, the input matching, and the gain as an output of our simulation. Okay. So now we need to find the IIP3 for this circuit. For the IIP3 simulation, we can add two tones to our input source. So first tone we can add a frequency of 0.545 gigahertz with an amplitude, let's say some P in. We can add another tone at 1 megahertz apart with the same power. Let's keep some nominal value of minus 50 dBm. So for the IIP3 simulation, we need to perform this harmonic balance analysis, which will take care of the large signal effect and find the IIP3 compression. In this test, we will define two frequency tones, at 2.45 and 2.451 gigahertz. And for the IIP3, let us also sweep the input power. So we'll sweep from minus 50 till minus 30 dBm with a step size of 5 dBm. Now let us plot the IIP3. So here we are sweeping the input. So let's extrapolate from minus 50 dBm. Here we need to choose the third order harmonic, which will be at 1 megahertz away from our input tones. The fundamental will be at 2.45 and 2.451 gigahertz. And we will be finding the IIP3 corresponding to the output node Vout. Okay. And here we can see that the IIP3 is coming out to be minus 15 dBm, which is very close to minus 16 dBm, which we derived for meeting the in-band blocker specification. So now we can see that we are getting a gain of 35.8 dB while having a matching better than 10 dB and noise figure which is close to 1 dB. And while doing so, the IIP3 is coming out to be minus 15 dBm. So all these specs are very desirable specs, and other than the minus 9 dBm IIP3, which is needed for the maximum input power specification, we are meeting all the other specs. So to improve the IIP3 further, we can connect a Rent mode passive mixer at the output of this LNA, so that the swing at the output node is going to reduce, which will improve the IAP3. Also, what we can do is, since the minus 9 dB IAP3 we need only for the maximum input signal strength, we can add a resistive attenuator at the input itself, which can be controlled digitally. So when the input signal strength increases, we can increase the input attenuation so that the overall gain comes down, which will also improve the IAP3. So for now, so this looks like a functional LNA, and we can see that there is a scope for a lot more optimizations, but this can be a good starting point.